It's on. Okay. Good evening, everyone. Welcome to our monthly seminar series on quantitative finance here at the Fields Institute. Before introducing our speaker, I'd just like to say thank you to our sponsors, Scotiabank, through the Center for Financial Industries, and Waterfront International for their continual support of this seminar series in particular. So today, it's a great pleasure to introduce Erick Delage from HEC in Montréal, and he'll be telling us about toward data-driven, what is it exactly? Data-driven equal risk pricing. So Erick, the floor is yours.
Everyone hears me? Online also? I assume so. So thank you very much, Sebastian, for inviting me to give this seminar. It's a real honor for me to be here. So I'll be presenting some work with my recently graduated student, Saeed Marsban, who's currently a senior consultant at Ernst & Young, and a colleague of mine, Jonathan Lee, who's associate professor at Telford School of Management. I'd like to thank Canada Research Share Program for the support, the financial support, and the Gerard also and Ivado. So today I'll be presenting some new methods that we've derived, algorithmic methods based on reinforcement learning in order to price financial derivatives in the context where we want the two parties involved in the transaction to be somehow sharing the load in terms of the risk of that they're being exposed by the derivatives. And we're doing this with the aim in the long run to be deriving option prices and hedging strategies that are purely driven by the data instead of being driven by stochastic processes assumptions. Okay. So let's start, and I'll start very simple, and throughout the talk I'll be talking about this very simple European call options. So I can introduce my notations here. So the payout of this option is the maximum between 0 and the value of the asset at maturity minus the strike price. And you see that if we're trading this option, there's two sides to this transaction. There's the buying side, which is worried about perhaps the asset price not going beyond the strike price. And in that case, it's going to have lost the transaction expense. While on the other side, the writer of the option, which is typically a bank, he's exposed to the opposite risk of what if the asset price goes beyond the strike price, and then he has to pay out this option, right? We assume you all know about this. Traditionally, the way options have been priced is assuming complete market environment. And I know this is a very basic environment to describe, but I want to give the basic principles that are replicating the complete market pricing strategy is based on no arbitrage assumption. And it's exploiting the fact that when the market or the asset process is simple enough and the market is frictionless, well, you can actually replicate the option payout using a portfolio that is hedging the risk of the options. So here are very simple equations in the context of two scenarios where we see that the only appropriate price for this option is sigma star S plus zeta star. Okay, so this can be applied in a more multi-period setting or in continuous time, as long as we can make this assumption that the market is complete, meaning that for any payout function, we can replicate the payout using a hedging strategy. In reality, it's very rare that the markets are complete. The moment you introduce transaction costs, this hypothesis fails. Here you have just a little augmentation of my example where I add a third scenario and there's no more replicating portfolio anymore. Okay, so this is one problem we encounter in reality. The other problem is that we don't know what is the stochastic process in reality. We don't know, even if there's two scenarios, what is the value of the asset in the good scenario or the bad scenario. Okay, so this talk will try to address these two issues. But first, let's go through what are the methods that can be used for pricing option in an incomplete market. When we survey the literature, we see two big categories of approaches. The first category is trying to draw as many insights from the complete market setting, namely the fact that you can price using a risk-neutral martingale measure. And then the question is, what martingale measure should we use, since the process itself doesn't give rise to a unique one that can be used for pricing. So they will use other market data, or you could use existing options to calibrate your martingale measure. Or you could also look at the physical measure and try to find a martingale measure that is closest to the physical one. So we won't be going into these directions because we're really worried about the hedging problem. We're thinking that whatever price we sell this option at, we'll have to manage the risk associated with the option. So from that perspective, you have different categories of methods. So some methods are, like the first in the list here, takes the point of view of the writer of the option, saying this writer will not come into doing this transaction unless the price is such that after trading the option, he is able to hedge completely the risk out of this option. And this gives rise in some context to expected utility and difference pricing. These are prices for which the expected utility of the writer is the same whether he trades the option or not. Okay? There are models that are more based on the arbitrage principle, or trying to minimize as much as possible using the hedging strategy, the error in replication. Okay? And these are called Epsilon arbitrage models, and I'll give you an example in a moment. So our method will fall into a very recent category of pricing scheme, which is called equal risk pricing. This was introduced in 2017 by Guo and Zhu. So if we look at the Epsilon arbitrage model, which is somehow the most closely related to what we're looking at, because it really tries to see the problem from both perspectives, either over the cases where the replicating portfolio is above and cases where the replicating portfolio is below the payout function. So you see here that the idea is to find a price for the option that allows me to use a self-financing hedging strategy that will bring the value at the maturity as close as possible to the payout function that I'm trying to cover. Okay? And what do I mean by as close as possible? In this context, one would use the expected square difference between the value of the portfolio at maturity and the payout function. Okay? When you solve this problem, you have two products from your computations. First, you'll have a hedging portfolio that allows you to get very close in terms of value to the payout. And second is the price of this portfolio. And you could interpret this price as being the option price. This was extended to a more risk-averse setting in Bandy and Bertsimas 2014, where they now use robust epsilon arbitrage. So what does this mean, robust? It means that instead of looking at the average square difference, we really worry about the tail of the square difference. So how large can that be? And we want to shrink this as much as possible. Okay. What is the advantage of epsilon arbitrage models? The first one is computational tractability. Namely, with the robust epsilon arbitrage, you can solve this using dynamic programming, or there's tools you can use from the robust optimization literature to address the problem. The resulting price that you get is also reduces to the no arbitrage price if the market is complete using that method. And you can think of it as if there exists a portfolio that can match the payout, well, then you can bring this error to zero, and you'll recuperate the price in a complete market setting. If you don't have a complete market, you can interpret the minimal expected squared error as being a measurement of how incomplete the market is. Okay? And from this, you get also a way of hedging. Okay? We'll have a look at this in an example here, where I really have just one point of time. I can compose a portfolio at time 0, and I let the stock evolve until the maturity. And this is a very simple setting, but we see things emerge in this incomplete market. The asset value here is assumed to be uniform over an interval at the end of the horizon. So obviously, the market is incomplete. If you apply the epsilon arbitrage model in this setting using the robust epsilon arbitrage approach, which looks at the worst case error, you get different prices for the strike price, depending on the strike price. And you see that there's a region on the right-hand side here where the strike price is at 120, and this orange line is actually going below the dotted line. The dotted line is the sub-hedging price. This is a price for which, if the option is traded at this price, the buyer has a way of composing a portfolio on this market that produces, with probability 1, strictly more revenue than the cost that was incurred by acquiring the option. So this is considered to lead to an arbitrage because someone could exploit this to make profit at no expense. Okay. So what we'll be presenting left in the next section will be the equal risk price, and I give you already I don't want you to be surprised later. I give you already all the results. The equal risk price will remain within the two boundaries of the sub-hedging and the super-hedging price. What really interests us is not only the fact that it can give rise to arbitrage, it's also the fact that it might expose the writer in particular, but also the buyer to unnecessary risk, or a risk that is very different from one perspective compared to the other. In particular, here's the same example where we compare the worst case loss after the transaction at the Epsilon arbitrage price. And we see with the dotted orange curve, what is the worst case loss for the buyer, and with the dotted line curve, what is the worst case loss for the writer. So from this, we really observe that the worst case loss is much worse for the writer than for the buyer. And this is because somehow the expected error, squared error function, it doesn't distinguish who's manipulating this hedging portfolio. Of course, the writer doesn't really care for how bad the replication is if the replication is giving him more value than the payout he has to pay for. And it's the opposite for the writer. The buyer doesn't care if the replication gives him gives the writer more payout than the option. So the fact that this function is symmetric and that somehow this approach only gives you one hedging strategy is problematic. So in the rest of this talk, I'll be talking about two different things. So first, talking about fair pricing. So we'll present this equal risk pricing framework. The work that we've contributed to in this field is to say what happens when we use convex risk measures. And we'll be computing a price that exposes both sides of the transaction to the same amount of risk. Okay? Then I'll give you some assumption that allows me to write dynamic programming equations for this simple European call option. And we will look at the quality of the price and the hedging that we obtain through the approach on a geometric Brownian motion that is traded in discrete time, and where we're using, again, this notion of a worst-case risk measure, meaning the worst-case realization of the liability. In the second part of the talk, I will continue talking about equal risk price, but you can also listen to that talk thinking about portfolio management or option hedging. We'll be thinking about how do we hedge a payout of an option. If you're managing a portfolio, you just don't have any options. You're just manipulating a portfolio in order to generate wealth. Well, how do we hedge an option without having to make an assumption about the stochastic process? Can we use directly historical data and learn from the data the statistics that are necessary to identify optimal policies for the investments? Okay, and in this context, we'll be extending a very simple and very popular deep reinforcement learning method to the risk-averse setting, where we're using dynamic expectile risk measures. And I'll give you some preliminary result on how this reinforcement learning method actually works on a geometric Brownian motion. So this is an overview of what's left for today, what's the plan for today. So the first section will be aligned with my first objective, and the last section will be about this deep reinforcement learning method. So if you're interested in looking at more details about this work, the first two sections, I encourage you to look to scan this QR code. It will also appear at the end of the talk, and you'll find a quantitative finance article that describes everything that I'm talking about. Okay, so let's start with trying to do equal risk pricing, first with convex risk measure. So what's a convex risk measure? I don't want to lose anyone in the audience. So first, historically, coherent risk measure were introduced. So this is introduced in 1999, and it tells you that if you're measuring risk of a liability, well, you want to map the liability, a random variable, to a scalar, and this mapping needs to have some nice property. If we don't satisfy these properties, the measurement could be misleading in terms of trying to hedge a risky situation. So what are these properties? And really the most important property for what's coming next in my derivation will be the translation invariant. So we can start with that one. That one says that if I have a liability X and I inject money in this liability, the risk should be reduced by the same amount that I just injected. Okay. Other property which are really important, monotonicity. So if I have two liabilities and one is guaranteed to generate more losses with probability 1, it should be riskier. And this is an important one, which is not necessarily satisfied by mean variance approaches. Subadditivity says that if I have a sum of two liabilities, the risk of the sum should be smaller than the sum of the risk. And finally, positive homogeneity, saying if I scale the liability by lambda, the risk should be scaled proportionally. Okay? Normalized risk measure, the normalized risk here just is a special case for is implied by positive homogeneity. If you replace positive homogeneity by subadditivity, you get and subadditivity by convexity, you get a convex risk measure. And this was kind of somewhat surprising, where we discovered later that there was maybe a more general class of risk measure that was also interesting. So what's convexity? It's the risk of diversification should be encouraged. Namely, if I do convex combination of two liability, the risk of the result should be smaller than the convex combination of the risks. Okay, so to give examples, convex risk measure, if you've heard of entropic risk measures, this is a measure that falls in that category. If you've done expected utility with an exponential function, this is a convex risk measure. If you've done expected shortfall or CVAR, this is a coherent risk measure. We'll be introducing another coherent risk measure later on, which is called the Expectile measure. So I don't know, this just as a heads up to make you interested about what's coming up. Before I can talk about equal risk, well, we won't put the two parties face to the same risk. So we'll talk about the minimal risk of each party. If the transaction of the option happens, well, there's money that goes from the buyer to the writer. And the writer is able to manipulate a hedging strategy, a hedging portfolio, in order to reduce as much as possible the risk of the liability that he's just committed to. Right? So this is the first problem here on the top. It says the minimal risk for the writer, if the transaction is at a price W0, is the lowest risk he can achieve by trading with in the market the asset, okay? Starting with a wealth of W0. At the end of the horizon, at maturity, he's left with a liability that involves the payout of the option, from which he can deduct how much money he made from the market, or how much money he lost from the market. The situation is reversed for the buyer of the option, which starts with a loss. He just paid for this option, so he's losing W0. But at the end of the horizon at maturity, he's going to be winning the payout. So this is in terms of liability. So the liabilities is negative F, and minus the reward, the returns he gets from his investment. Okay, so this gives rise to what I call here these var rho W, var rho B, which are the minimal risk at price W0 for the writer and the buyer. What do we want to do with these two elements? Well, we can now define the equal risk. What's the equal risk price? It's the price at which the two parties, if they hedge in the market appropriately, they are exposed to the same level of risk. Okay? In practice, we all know that probably the bank is hedging the payout of the option, maybe not the buyer, right? The buyer is buying this for other reasons. He has other risks that he's trying to cover with his option. But this price still makes sense because the buyer could be hedging the option using the market. So without knowing more about the buyer's situation, this is all that we can discuss about. Like if I give you this option, you might hedge it. You are able to reduce the risk to this level. So why should I reduce my price further than this amount in terms of from the writer's perspective? So this will be the price that we're talking about, this equal risk price. Okay, so how do we compute this equal risk price? Well, first of all, there's this notion of fair price interval. You might have been exposed to work of Bernard et al., 2013, that introduced concepts of fair price interval. So this approach is describe an interval that is within the super hedging and the sub hedging price. It's saying if I fix the writer's risk measure and I fix the buyer's risk measure, well then there are prices for which each of them, or if they hedge properly, can bring the risk below zero. Okay, so the fair price interval for the writer will be the largest price at the lowest price, so that he has a way of, after accepting this transaction, hedging his risk out of the problem. The same thing for the buyer. If he do a transaction at W0B, he has a way of hedging in the market so that at the end of the day, his risk is below zero, meaning that he might as well buy the action, that there's no loss in buying this option. Okay? By translation invariance, and I'm not giving you the details of the proof for sake of time, you can actually demonstrate that the boundaries of these fair price intervals are actually directly related to the minimal risk at the transaction price of zero. It's going to be, the upper bound would be the transaction, the minimal risk at zero for the writer. The lower bound will be the negative of the minimal risk at zero for the buyer. The equal risk in this condition will exist if and only if this fair price interval is bounded, and it will be equal to exactly the middle of this interval. So it's a very simple result that if you find the boundaries of this fair price interval, which only requires you to find the hedging strategy for an initial transaction at price 0, you get the two boundary, and you get the equal risk price as the middle point. And this, also by extension, leads to a price that will be protected against arbitrage. It will lie in the what's called the no arbitrage interval. So going back to our illustration before, we see that the fair price interval for any strike level is this triangle, the blue triangle. We saw that we were worried about epsilon arbitrage that was going beyond this fair price, this no arbitrage interval. And we see that, well, yes, indeed, the equal risk price, as I've drawn it, is exactly in the middle of the two boundaries. Okay, this is in a worst case risk measure setting. If I'm using a CVAR setting, well, then the region that is blue, the fair price interval region, will be within this triangle. But here we're looking really at the worst that could happen, which is if both parties are worried about worst case, then these things simplify and we can have a nice intuitive illustration. Okay, so how do we compute this? This is the main question. So the approach we will use will assume discrete time trading. I'm really a discrete time person. I like formulating optimization model, dynamic programs, and working with these type of tools. So we'll assume we can trade k different time point between the transaction and the maturity, which gives us a feasible set for the self-finance hedging strategy, which is denoted by X bar. Note here that in this X bar, the controls are at each point of time, how much asset am I putting in my portfolio? So then you start with the initial transaction price, which is for the writer W0, and you add to it the revenues you're gaining from owning the asset for a certain amount of time and seeing the evolution of your wealth. Okay, I'm getting on the way of getting dynamic programming equation, but remember, I only assume here that these risk measures were convex risk measures. In particular, to go forward with this work, I will need to make some assumptions that will allow me to write Bellman equations. And for this, I need the following, to make the following assumption. First, that I'm dealing with a convex dynamic risk measure. So in Rusinski and Shapiro in 2006, they introduced the notion of conditional risk mapping. So, and this is really useful if you're trying to get a measure that is dynamically consistent, meaning that at any point of time as you go along, you can motivate the optimal plan that you have for the future simply by applying the risk measure from that point on. Okay, so we have a nested structure for the risk measure where we're nesting inside each other conditional risk mapping. So conditional risk mapping will take a random variable from a certain will map back a random variable in terms of the condition that it was that was imposed on the conditional risk measure. Okay, this conditional risk mapping will assume satisfy the same properties as we were imposing on the original risk measure, namely convexity, monotonicity, and translation invariance. If you're dealing with a coherent risk measure, also scale invariance. Okay, so what's another hypothesis we have to make? Well, it's possible that I have this nice nested formulation. For example, here I give you an example of CVAR, where I'm taking the CVAR of the CVAR given that the asset has now a value S1, of the CVAR of assuming that now given that S1 and S2 have been observed, up to finally this X variable, CVAR of X, given that I've seen almost the whole history of this asset value. Okay. So this is the nested structure. But this is not enough to have a dynamic program that has a low dimensional state space, because you might have arbitrary, like here at this point, I would need to keep the whole history of the asset value process in my state space in order to compute things. Okay, so we make a second assumption that the conditional mappings are such that given the history up to time k, I can measure the risk of X using a different risk measure that only depends on a statistic of the history. Okay, and this statistic will be what will replace the whole history in my dynamic program. Particularly at the bottom here, we have the typical Markovian assumption on on a process, which allows us to discard the history if we have the right statistic on which for which we are Markovian. So this being said, I laid the equations here. There's a lot to parse, especially, but already maybe only half of it is interesting because the rest is, we have two versions of this model. If I start with the writer's model, what do I have? I have at time k, I know everything about the past or all the statistics that is relevant about the past, so I can simply evaluate the payout. If I go backward one time step, I'll be measuring as a value function. I need the state in my equation because I need to keep it in order to evaluate the payout at the end. But in order to predict the dynamics, I only need to keep the statistics. And I can impose the risk measure that is conditional on the statistic, measuring the risk of the return that are generated by my investment, negative of the return, plus the risk to go starting from the next time point. And this is the nested structure that allows me to write this way. The same is happening for the buyer, except that the buyer finishes with the negative payout, since it is now a revenue and we're casting things in terms of liabilities. And once we have the solution of these dynamic programming equation, we can simply evaluate the value function at time 0 for the initial state of the asset value and the initial statistic, which will identify the upper bound of our fair price interval. The lower bound is the negative of this amount. And if we take the midpoint, well, we'll get our equal risk price. So solving for the equal risk price involves solving two dynamic programming problems. So let's see this at work in terms of a problem. We'll be using a geometric Brownian motion in a moment. But before I get there, I'm really from a robust optimization point of view at this point. I'm looking at the future stock asset value process as being simply a vector. And this vector has to lie in some uncertainty set. Okay? So my risk measure here, I interpret it as being a worst case risk measure. It's looking at the support of our distribution. And I'm looking at the worst case realization of my liability for any realization on the support. Okay? The buyer and the writer could use different uncertainty set. We'll be choosing the same uncertainty set for both. And this gives rise to a robust dynamic programming problem that we can solve by discretizing the state space. So the application here is really the first type of test you would want to do with this type of technique. Namely, I'm dealing with an asset that evolves according to a geometric Brownian motion. The drift is 0.07, the volatility 1.13, and I'm looking at a 1-year maturity. I'll give between 100 and we'll see 225 periods at which we can trade, meaning that although it's a geometric Brownian motion, the market is incomplete because I cannot edge continuously. Both writer and buyer is using the same uncertainty set, and the uncertainty set, I usually present the details because it's important to design the uncertainty set the right way. There's a lot of technical aspect there. I push this to the paper if you want to have a look. We can also talk about it later. But just think of it as there's an uncertainty set with a certain parameter that I can scale, which is gamma. And I'm scaling this parameter so that it covers, in this experiment, 95% of all the trajectories that the asset can take. Yes? Yes, so the question is where the risk measure went. I see this as the risk measure here. Yeah, the fact that, but you could write this as a soup somehow where you're looking at the support of some distribution, but what I care about this distribution is not all the density, but just where does it land. And there's a bit of a stretch here because here I'm saying it's the S soup, but then I'll be calibrating my uncertainty set based on a confidence level. So there's a leap of faith there that needs to happen in order to interpret what's going on. Okay? So if we could, we would do full support, but perhaps full support, distribution can have infinite support. So then we need to take something more reasonable. And we can always play with this confidence level to represent how risk averse each parties are. So do they just want to cover 50% of the trajectories or maybe 99.9% of the trajectories? So this is what we produce with this approach. The important rows of this table is the equal risk price and the Black-Scholes price. So Black-Scholes price would be the right price if we were trading in continuous time. Here we're using it just as a reference, and somehow as we're discretizing more and more, we should converge to the actual price should become the right price. Okay, so what we see is that our equal risk price in this setup, in this setting, is always higher than the Black-Scholes price. So this indicates that the hedging strategy from the Black-Scholes price somehow exposes the writer to more risk. And our equal risk price is saying, well, you should increase this price actually if you want the risk to be well distributed between the two parties. So this is for a call option. For different other type of option, you might have the opposite effect. Okay, but you can find out by computing the equal risk price. What we saw, which was very encouraging here, is that the pair price interval, which is really just based on this 95% coverage property of our uncertainty set, it still seems that it's converging to the Black-Scholes price. So it's getting closer to the Black-Scholes price. Of course, like we cannot go for larger amounts of 225. There's more work to be done to make this scalable to perhaps 10,000 trading points. This is maybe left to verify and validate, but this is very encouraging that we seem to be narrowing down and getting closer in terms of boundaries. So yeah, and I didn't give too much details. So ITM, I don't know if it's an acronym you all recognize. So there's an in the money option, an at the money option, and an out of the money option. Okay, so what else can we say? Especially like, what does it mean? What do we gain by being equal risk? By having a price that leads to equal risk? I'll start with the graph on the right. So on the graph on the right, we're giving for different percentile level the percentile value difference of the liability obtained by the equal risk price or the Black-Scholes price. So by difference, I mean that we have two parties, the writer and the buyer. And if I run these hedging strategy, they'll be exposed to different risk and I can different liability overall. And I can measure the quantile and compare the two quantiles, the 99% quantile for the writer, the 99% quantile for the buyer, and I show the difference here. So when we have low quantiles, Black-Scholes equal risk price seems to be inadequate. So why is it inadequate? Well, I use this worst case analysis, which was really focusing on equal risk in the large quantiles, not equal risk in the low quantile. As we increase the quantile rank, we see that the differences between the same quantile for both parties become smaller as I increase. And for the Black-Scholes price, it's actually the opposite that occurs. So given that I'm using a 95% confidence region, it is the high quantile level that are really worrying me. And we see that we do get an edge there. We're able to rebalance the risk for those quantile levels. On the left-hand side, we see something about the average percentile value. So if you're just interested in, on average, are the two parties exposed to more or less risk? We see that, again, the same type of behavior, that Black-Scholes price is much better when the quantile is low, but it's becoming outperformed by the equal risk price for high quantile level. Now, this graph would be also interesting if we looked at other type of risk measure than the worst case risk measure, but already here we see signs that when we care about the worst case losses, then the equal risk pricing is able to balance things more appropriately. Okay, so the last part of the talk is based on, I'm going back to this idea of towards data-driven pricing or data-driven hedging. And as we've seen, the option pricing problem for equal risk price was required us to solve two risk-averse hedging problems. So we'll do this here using reinforcement learning. So before I introduce the methods, I'll go back and introduce the notation of Markov decision processes. And this is especially important because we're not just going to take an off-the-box, off-the-shelf algorithm and plug it in. There are no algorithm really that works for risk-averse MDPs right now if you're using dynamic risk measures. So this is really active research, and the methods are being developed, deployed, evaluated. So there's a lot to do in this field. So let's look at the finite horizon MDP. We have a set of state, a set of action, a reward function that depends on state action and the transition that was obtained, and then an operator P that models the dynamics of the system. Okay, our objective is to find a policy that maps the state and the time to an action. And if we just run this policy, we'll obtain a random sum of cumulated reward. This is captured by our R tilde here of pi. So our risk-averse MDP will try to find a policy that minimizes the risk of the cumulative reward. So we apply a risk measure on this minus R tilde. Okay, and what we saw before is that the type of risk measure we would like to work with are dynamic risk measures, right? How is this related to equal risk pricing? Well, we can actually massage our equal risk pricing problem so that it actually fits into the risk-averse MDP setting. Namely, remember we had to solve two hedging strategy problems, one for the writer, one for the buyer. This will give rise to two risk-averse MDPs. Each MDP have to do with a state space that keeps track of the asset value and the state of the Markov chain. If I know that the underlying process is Markov, then I would like to keep track of this state. And an action that is here modeled as being how much do I invest in every stock. So just an interval -1 for every asset. Finally, the reward will be for any time t smaller than t, we obtain the return from our investment. And at time capital T, we have to, sorry for the notation here, this should be S capital T. We obtain the payout of our option if we're the buyer. If we're the writer, well, 1 minus 2 will give you the negative payout. Or the opposite. The payout will be a liability. So for the writer, it's going to be, what's going on? Oh, it's all in reward. So now we're casting things in terms of reward. So the liability becomes negative for the writer, and is a positive amount for the buyer because he's getting this payout in his pocket, and reward is that. Okay, so we have two different risk-averse MDPs. We know that we want to use dynamic risk measures, and here I won't want to use a worst-case risk measure. I want to do something more, maybe more like easier to understand or easier to adopt than always worrying about worst-case scenarios. So I'll be using a special type of risk measure. But what should I use as a dynamic risk measure? Our choice will be specifically aligned with whether there exists or we can think of an algorithm for implementing it. The initial work in risk-averse MDP, they wanted to tackle too much large class problem as possible. So they looked at general dynamic risk measures that are coherent, and they said, oh, look, these dynamic risk measures, we can cast them as robust MDP because we know that there's a worst case expected value representation for conditional risks. And if we have a robust MDP, then perhaps we can exploit this, the structure of robust MDPs. This first work needed a simulator that would re-simulate conditional on a state, be able to re-simulate the transition. And even re-simulating in a reweighted way, maybe doing importance sampling or something. This was improved by Wang et al. In 2021, where they designed a policy gradient for on-policy learning. So on-policy means that you will learn as you are acting. And then since you're learning as you're acting, you don't control really which state you reach, and you have to learn from the state transitions that you're obtaining. You cannot simulate. The problem there is that there was 5 different neural networks in this approach. There's a network that controls your policy. How much do you invest? There's a network that tries to estimate what's the value of what's about to happen, the cost to go. And there's 3 other networks that are there somehow to model the robust aspects. So there are adversarial networks that are trying to find what are the best reweighting of the reward that will model this dynamic risk measure. So a very complicated approach. In 2000, I think it was in 21 or beginning of 22, we found a very simple modification to deep deterministic policy gradient to handle a very specific class of risk measures, dynamic expectile risk measures. This is important because this algorithm has more than 10,000 citations right now. It's a well-established algorithm. People have designed improvements on it, and it's being deployed for important problems in reinforcement learning. It addresses the risk-neutral setting. How can we make it risk-averse? You'll see it's 1 line of code. Finally, and I'm very happy to be presenting this here. I hope this can create new synergies with the research that's being done in the statistics department here. There's this work, local work, Coach et al. Involving Sebastian, that proposed, extended somehow what we did, but for a general class of dynamic risk measures. What they exploit is the fact that some risk measures are conditionally elicitable. Maybe we can have a discussion about this afterwards. we'll see how somehow it requires, to go beyond what we did requires more machinery. So why use expectile risk measure? Well, let's backtrack and remember that expectile risk measure were somehow invented in order to solve the problem of elicitability. The same paper that defined elicitability of risk measure came up with, hey, look, expectile risk measures are solving this problem. It's the only measure that has this property. So what is elicitability? Well, it says that risk measure is elicitable if it is the minimizer of an empirical risk problem. Okay, so here my random variable is x, and I want to find the q that is closest to x, but somehow with respect to a loss function. Okay, if you have a squared loss function, just a square, you recuperate the expected value. We all know this, or at least you learned today. Otherwise, you can also use a piecewise linear function, and you get the quantile of x. Okay, and the quantile level is parameterized by tau. So why is this important? Well, it's actually part of elicitability property to say that if I get data, I'm able to, from the data, identify whether my expectile estimate was right or not, and if it's wrong, I can steer it in the right direction. Okay, so if I have a bunch of historical data xi, yi, later on, what will this be? This will be xi will be the state. It will also include the action, but let's just think about the state, and yi would be the realized risk to go, a sample from the risk to go. What do I want to do? I want to measure the conditional risk of y given x, but I don't know what's the conditional distribution. Well, these elicitable risk measures are saying that this risk can be estimated using an estimator. So think about this maybe as a linear function of your state x, and you get the right estimator if you train this estimator using the right loss function. So if you use an affine function here of x, and the theta is the parameters of your affine function, and you use the loss function for expected value, well, the estimator you get is measuring the conditional expectation. If you're using the quantile loss function, you're doing quantile regression. Okay, we want this because we want to learn from the data what is the risk to go. So we need to estimate it using as a function of the state. Okay, so going forward, if you want to use a coherent risk measure, such as CVAR, well, CVAR is not directly elicitable. You'll need to use an expectile risk measure. Okay, and the expectile risk measure has a special loss function, which is piecewise quadratic. If tau is equal to 0.5, you get back your expected value. If tau goes to 1, you get the worst case. So tau allows you to control the risk aversion. Can I see that I maybe have 5 more minutes, or we started late, or yeah? So I'll try to maybe I'll skip a few slides. So we can write. We can then extend this expectile risk measure to the dynamic setting. Well, we're going to nest them. At any level, I would condition on the history of the MDP, and I can measure the conditional risk of a random variable here, Vt plus 1, which is the risk to go, given that I've done this trajectory up to this point. Okay? So this is how we define the expectile, and we can obtain very similar dynamic programming expression as we had obtained before, but in terms of a Markov decision process. Right? Remember last time we were looking at the reward was the return I get from my investment, and then V pi was the risk of pursuing my hedging strategy forward. By using interchangeability property, we can actually also derive a Q function, which is an operator that allows you to estimate the risk to go. If you start in state ST, you apply action AT, and from that point on, you apply the best hedging strategy that you can think of. Okay? So this can be modeled recursively in terms of the next Q star T plus 1 function. Okay, so here's the algorithm. So in its risk neutral setting, so remember tau equals 0.5, there's already a paper, 2015. It's been applied extensively. It does two things. On one side, it has, you see over here, a neural network parameterized by theta q that depends on the state and the action. So this is what's called the critique. So this one is in charge of estimating what's the risk to go if I start in S and I apply A, and then I do the best I can. The other neural network serves as the policy. The policy here is my hedging strategy. It depends on the state, and it's going to be parameterized using theta pi. Okay, so there's two things to update in this DDPG algorithm. How do I improve my critique network, which is trying to give me the best estimate of the risks to go? And how do I improve my policy, which will look at the critique and say, well, for this critique, I should improve by doing this type of action in this type of situation. So what they do here is the critique step is it's just following gradient descent along the policy network. It's not so sophisticated. And what we'll really pay attention to is this step for updating the critique network. This was the policy network. So the critique network, and really what you're doing there is you're taking a step in the direction of the derivative of L with respect to your current critique minus what you observed in terms of risk to go sample, and then multiply by the gradient of the critique with respect to its parameter. When you have the loss function being the quadratic function, this here is the TD error, and reduced to very simple, this is the DDPG algorithm. When we are using Expectile, dynamic Expectile risk measure, we simply have to pull out the square difference from the algorithm and put in our piecewise quadratic equation. So the gradient, the derivative here will be slightly different. It will adapt to the level of risk aversion that we have. Again, remembering that it's tau that controls this risk aversion. So let's look at how this plays out in practice. We're again in a very simple setting using geometric Brownian motion. Initially, this setting is there to tell us, well, this setting, I know how to solve the problem. I can discretize my dynamic program. So I can get these orange curves that are the true values at optimality if I was able to solve this perfectly. So in this context, we have two sides here, the writer and the buyer, and we have the risk that is being exposed to when you follow the policy obtained from the reinforcement learning agent. And you see that these curves are very close. It seems like for the buyer here, our network was slightly inaccurate and loses a little bit in terms of risk exposure for the buyer. We also compared to some work that was concurrent with ours, and this is really active field of using reinforcement learning for hedging. And the type of work for which there's the most algorithms in reinforcement learning are situations where you've got a static risk measure. So instead of having this nested structure, you impose maybe a CVAR over the whole random variable. In this, you don't have dynamic programming equation, but you might still get the policy gradient method to work. So we see here that we get an exposure to risk in terms of static expectile. And at maturity 12, the two methods pretty much exposed to the same level of risk. But the issue with static risk measures is that they're not dynamically consistent, meaning that if you find yourself 6 months later implementing the static risk measure policy, you'll be exposed to more risk than if you were trading the option on that day and finding a new hedging strategy for the option. So you see that the dynamic risk measure is able to get better risk as time goes along and gives an incentive to deviate from the policy that was actually proposed by a static risk measure. This also tells us that once I solve the problem for dynamic risk measure, I have a policy that works for any maturity, right? Because I could think, okay, what if I have 6-month maturity instead of 12? I'm still in the same state, so I can run this, I can compute this price and I can compute the hedging portfolio. This also works for the strike price, because usually you also include in the state space the amount of accumulated wealth. So if your strike price is different, you can adjust the state accordingly and get the policy for that. So finally, this is the only thing, the approach situation in which we looked at more complicated models. We were working with a correlated geometric Brownian motion. It was calibrated using 5 different stocks. And again, we were comparing the same two methods, the dynamic risk measure and static risk measure. In this context, it's much more hard to identify whether these reinforcement learning approaches have converged to their best, the best they can produce. But given the state of what we could deploy here, we see that the two methods somehow perform more similarly in larger scale problems. Okay, but still, I think these are very interesting methods to try to deploy and experiment with in a context where we don't want to make assumptions about the underlying asset process. So this leads me to my conclusion. So the main takeaway message is twofold. So first, I want you to remember that when you have an incomplete market, it is possible to price in a way that both parties are exposed to the same risk. The technology is emerging. There are mathematical constructs for doing that. What we showed was that for convex risk measure, it was not much more difficult than to hedge the option itself. We just have to find a hedging policy for the two parties. And we showed that it corrects for some inequalities that are obtained when you use a risk-neutral measure or if you use an Epsilon arbitrage model. The second message is that I'm hoping that in 5 years, about 5 years, we'll be able to do option hedging and portfolio management directly from the data using reinforcement learning. And if we want to be risk averse, which we should be, these methods are in development, and I think there's still a lot of work, but there are already some methods that are worth experimenting in different contexts. And anyone that wants to collaborate on this would be more than welcome to get in contact with me. Well, the last point here I described already. For dynamic risk measures, when you train these methods, it can take a long time, but once they're trained, you can apply them for different maturity level, different strike price, so they're very versatile in terms of application. So thank you very much for your attention, and I'm happy to answer any questions. Again, the QR codes for the two papers are there. Thank you.